with partying elderly. It doesn't take much.
It was like SWAT.
It was Bumpets was playing.
Oh my gosh.
Sanger, and we had all these people in Hawaiian shirts.
Okay. Okay, let's get started, everyone. Looks like the attendance is slowly dropping.
I've been here every class.
I've been here since 11 o'clock today.
Okay. Okay.
I've been here since 7 o'clock today.
So what do you guys say? Should we have
Attendance quiz? Yes.
Yes, something like that?
Field trip to South West.
Okay. Yeah, I realized that, well, when we get into December, then start to have people disappearing.
Seminar?
No, for the class. So,
See this space? This space is here every day.
yeah, every day.
I think Chris
And Rebecca?
Dan
is
lately,
outside.
too.
Yeah,
Okay.
I think Sam's the only one not here, and she's sick.
Okay.
Yeah.
I mean,
Everybody else, I think, is occupied with something. I think they're doing waterborne stuff.
but not at the class time, right? At
I
1:30.
don't know. They went to go talk to somebody, and I guess they got sidetracked.
Okay.
Maybe they ran into
All right. So why don't we do this? In the next class, we will do random attendance quiz, and whoever is not here may have a little bit drop in the final evaluation. I think that's a part of the requirement. If you are committed, please.
So, random attendance quiz, exactly, next class.
No, I cannot comment on that. But random. Great. So everybody, let's continue to our talk. Yeah, because I see Chris's bottle is here, so he should not be far away from that. So what we do for these two classes, two lectures, what are we missing and what we're going to talk about today?
Well, you did a wonderful job explaining spinodal and binodal curves.
All right. Is everybody on par? What is spinodal and binodal, and what the definition when they start to decompose? So I want to take the time at the first part of the lecture to re-emphasize the key point we chatted about in the last lecture. Is spinodal binodal for classical small molecular blend. Up to now, we haven't touched the polymer. Remember, in the Flory-Huggins theory, this is a tiny polymerization in the bottom of the equation. We haven't talked in the phase diagram. And in the second half of the lecture, we will talk a little bit about that in terms of spinodal and binodal decomposition. How does it affect when you start to talk about polymer, not just solvent, okay? The other thing I want to touch and finish and wrap up is critical point. What is a critical point for the solvent, and how do we get that part? Okay, so if we have a little bit more time, we will finish the lecture. Talks about what is it? Kai. I was distracted a bit. Kai, how's your afternoon?
It's good.
All right, good. Glad to hear. So we're gonna have a random quiz check. Random, okay, really random. Starting next lecture, because I realized that the attendance is slowly decaying. Or maybe just one. It was just me feel a little bit emotional, discouraged for my lecture. Oh.
Wait, there's going to be a what check?
Random
attendance quiz that may or may not appear anytime before the end of the semester.
Okay.
starting at 1:31 p.m. if it starts.
Yeah, 1:30 sharp every day.
I could never miss your class.
Otherwise,
it would be
you might
a
miss the
disservice to my whole experience.
All right. So it's a little bit sidetracked, but I wish I never need to do that. So what about what we talk about in the phase diagram? So we cut to the chase. We talked about two ways of having the phase diagram. Spinodal. Oh, my drawing is degrading every day. Let me get it better. It's not acceptable. All right, so better? We talked about how do we get this diagram. It's one of the most important picture in chapter 7 in your textbook is about the phase diagram. And what we can learn is if you blend A and B, if they will mix or not mix, and I don't need to put too much. So in the top, it's going to be one phase. In the bottom, it will be a two phase. So in other words, you can put a tiny bracket. It's going to be mixed. So this will not be mixed. So this is going to be a binodal curve, and this will be the spinodal. And we actually know this region is called metastable, where we left it at the last class. And we pretty much covered this grade part because we explained the other common plot you would be seeing a lot is instead of have temperature, we plot about free energy, delta G, versus composition, right, from 0 to 1. And this, we did some drawing showing like this, and how you can, from this curve, to get each data point on here. So you can think about this as one temperature at the temperature T. So this would be the temperature T. Let's call it T0. OK. So that's a phase diagram we learned. What we left is we talked about, you can get the second derivative of delta G to composition. You can get inflation point at these two. And these 2 points defines what are the spinodal temperature for your material, right? This is basically a transition point from a curve is concave up or concave down. On the left, this half of the curve is concave up. In the middle, these 2 points is concave down. So pretty self-explanatory. And in the textbook, we need to cover one more point for this data is what is critical point. Critical point is where the definition of the critical point is where the spinodal and the binodal point is met, or also known as in this binary phase, or known as the tip of your curve. For me, it's pretty self-explanatory. A critical point, you just look at a curve, then find what is x, c, or critical concentration. Or here, Tc is critical temperature, and that's the temperature you want to be at when your system starts to suspect to phase separate. Because above this temperature, every data point is in the mixed phase. Well, below this Tc, then if you change the composition from 0 to 1, you're going to cross the different phase from mixed to metastable to binary phase, then back to it again, right? So in the first half of the class, we're going to figure it out what is the critical point for a binary blend. Any guess what the xc is? No, not the chi. Volume function. Or the volume fraction for the first component. Or composition for one component at the critical point. Any guess? I think Michael might know it.
Of what the component is that what you're saying?
Let's say the minor component in this blend. So this bottom axis is basically plotted at volume fraction. I sometimes use interchangeably these xc and phi a. So it's basically says what the composition of phi a. We're mixing a and b here, right?
Mm-hmm.
So the question is, what is this?
0.5.
It's symmetric, yeah? Looks like 0.5, right? Right in the middle. Okay, let's figure out, use the first half of the class, see if that's the case. 0.5.
It can be skewed, right?
I'm not so sure.
Did you just say 0.5?
I did say
It was just a wild guess?
Now you're making me second guess myself.
No, it's a wild guess, but we also hear some of the other opinion, right? It might be skewed, right?
Can't the spinodal curve be shifted to the right or to the left?
Sorry?
Can't the spinodal curve be shifted to the left or the right?
Yes, it can be.
Change your.
And we will use the first half of the class to figure out when does this fit in Daniel's suggestion it's 0.5, or when does it to be skewed to the left and right, and why that's the case. And I have to say both of you are absolutely correct. In some specific circumstance, in that case, we will see it's strictly fixed to the solvent-solvent case. Or at the beginning of our lecture, we just talked about two of the molecular they're mixing. In the advice you gave, saying it might be skewed, that's also true, and that's related to the Flory-Huggins theory. Flory-Huggins theory. Remember, in the first part of the lecture, we talked about when you have a connectivity, you have an n component in the entropy contribution from a polymer, and that's where we will see in the second half of the lecture how this will be distorting the phase diagram whenever we have a connectivity or polymer contribution. Okay. So first half, let's figure out what is the chi-c, Tc. Let's put Tc, and what is phi a for a phase. For critical point, right? So that's a for phase curve at its critical point. Okay, so let's do this. Let's figure out. Nathan, what would you do if you want to find the critical point based on the theory we just talked about, where this is sort of the highest point on the curve, or when the
two different components that are spontaneously unmixing, I would heat it up until it becomes homogeneous.
Yes, but you need to do many. No, I mean that's sort of close to what I asked. I'm asking specifically, what if I want to know, is there, based on the physical definition of what we talked about, is there any chemical or mathematics way we can extract critical point?
Can't think of one.
So let's step back. What's the definition, or how did we find the inflation point or Spinodal point in these two? So we did something. I hear something? Second derivative of free energy of this, right? So we actually, in the last class, we took the second derivative of x1 is, this is definition for Spinodal decomposition. So the critical point in need, it's actually takes one more step. that's the third derivative of this equal to 0. Would be the critical point. Because that's where this basically the plateau point is. If you take one more derivative of the slope, you can find where it is 0. And that's roughly the definition of what is a critical point. Okay? So not too bad, right? Because we know what is a g, delta g, how does this relate to the x1? And I'm going to remind everyone, so this is just a Flory-Huggins, this is just a lattice theory while you mix the solvent. How does entropy and entropy contribution to this, right? So can someone help me? Would it be the delta G divided by RT?
Delta H minus T delta F.
Yes, and that is equals to?
I didn't get that far. Psi 1, psi 2.
Phi 1 ln phi 1.
I,
Phi 2 ln phi 2 plus phi 1 phi 2 phi.
yeah, actually that's great. That's exactly the Flory-Huggins theory, right? That's for mixing of the, basically the common component. So that is basically, we can write it as n1 log x1 plus n2 log x2 plus, and this is a chi, so that's not the x, this is a chi or Flory-Huggins parameter. And the other way, you just mentioned, that's the entropy contribution. That's the entropy contribution. Right? So we just rewrite what we learned before. And if you look confused, I know, it's because the system sometimes talk about per lattice site, sometimes talk about persistent. We know, because you only care the whole system, that's why we use the mole ratio or n1 multiplied by chi2 as the equation here.
Instead of using the phi's.
What is phi? Yeah, that's per lattice site. That's basically you divide by total molar number for component A and B.
Okay.
Well, what I taught that class I mentioned to you, I expect this could be a confusion point. Is it clear? So
Phi is per lattice site?
yeah. So is it good? Everybody on the same page? There's a question in the back.
Understand what per lattice site.
Oh, so let me use some time to explain. I know this day will come. So let's say you have n1 mole of solvent A, right? So you have n1 mole. How much number of total solvent molecular? Just count the number. So it will be n1 multiplied by R. R is Avogadro Constant. So 1 mole, which means there's about 6 to the 24 of numbers of solvent, right? So in the theory, when we talk about the lattice, we purposely say each molecule are going to occupy one lattice. Or like the chair in this classroom, every student going to take one chair. So I did it many times, this kind of curve, and I like drawing this again and again. So for the system, you have a total energy for the system. And if you divide the system by number of lattice, you will get the energy per lattice site. Okay? So then it comes in two ways. We can write the persistent or per lattice site in terms of delta G. Okay, persistent, that will be the one, n1 ln x11 plus n2 ln x2 plus n1 x2 and a chi. Right? So per lattice side, how many lattice side total? Well, we mix solvent A and B. So the total number of site is n1. So let's first count the number of site. So that's m1 plus m2 multiplied by r, k. Okay. K is, again, the Avogadro constant. So if you divide by this, use the top to bottom. So you will get this, n1 divided by m1 plus n2. I should write this as small n. Right? So we're going to divide this whole equation by this.
That's m1 plus n2 times k?
Yes.
Okay.
And I already moved the k to there, so you don't need to worry about that. n1 plus n2. And this is going to be ln x2 plus n1. Right? x2 and chi. So, and you see this is basically phi 1, or the volume fraction of the first part. So that's why in other way you can write is the equation is this way. Per lattice site x2 ln x2 plus x1 x2 and phi. So that's the difference. Per lattice side and persistent is basically something similar.
Are you using chi and phi interchangeably?
No, not chi and phi. Chi is chi. Phi, this is actually, I think at some point I wrote this x1 or phi 1 interchangeably at some point.
Okay, that's confusing.
Yeah, that can be confusing.
The x is right there. You also mean phi or no?
No, this is only phi, which I marked it.
No, I mean like behind you. The x1.
No, this is only chi. x1, x2 are just a volume fraction, or phi. Good? Yeah?
K is Avogadro's number, not Boltzmann constant in this case.
No, R is not a K is Boltzmann constant, and K multiplied by the other K, it's without this R. This is not the Boltzmann constant. That's a slightly difference between the KT and RT. We can talk a little bit in more detail what these numbers are. It's just this two constant number difference is multiplied by K, and I'll show you what I mean. So let's get back to this, and let's get this going. There's a little bit of mathematics, but depending on everyone's mood today, do we want to go through a little bit of detail, or we can just spend 10 minutes to explain some of the outcome? Oh, a lot of smiling face. That's a good sign.
I'm an outcome guy.
Huh?
So I'm an outcome guy.
Yeah, results.
Big picture. It's nice that you actually asked us this time, though.
So why don't we? Okay, then I wouldn't do too much math. I'll give you guys some of the conclusion. So it's a little bit tricky because you now need to derive it 3 times versus this xn1, right? So you need to have a partial derivative or free. So chemical potential will be equals to delta G divided by x1 at a constant at pressure and temperature. So you will see it later on while we talk about osmotic pressure section, where we talk about this. So this is called chemical potential.
Is that X or chi?
No, it's all X. If I have a chi, I'll specifically mention it's a chi. Okay? So these are just the volume fraction. So, all right, if you guys don't need much in-depth math, we will jump to the so this with two lines in the bottom, that's actually is chi parameter, okay? So if you derive this one, this chi will stay. And we give a small underscription of S just to, so that you guys can see the difference, chi volume fraction. Okay, we are halfway there. We still need to take one more derivative of it. It's just the first derivative, right? So how about we take a second one of this mu one? Getting closer.
Is that a 2?
Where is 2? Yeah, that's 2. Chi S. Volume fraction 1 minus volume fraction 1. Okay, good. We skipped the actual last step. Could be take 20 minutes to talk about that. But I think everyone had enough math in the first part of the lecture. So, and now we need to take one more derivative of this, then we are good to go. Okay? Okay, so what if we take one more time?
3 chi s minus.
So we take one more derivative of this we can write it as second derivative of chemical potential, derivative x1 square, right? So take one more derivative to x1. So we will see this will become minus x1 square, right? And the second part will become twice x s. This will be the chi. And when this equals to 0, we will be able to find what is the volume fraction of this one is, right?
Are you taking the derivative in terms of both of the x's, x1 and x2?
Yeah, they're interlinked. So if I take derivative of x1, I basically will consider x2.
Okay.
So I figured out, why don't I do this? I'll take a copy of my note, which has a detailed derivative, how I skip the 20 minutes in the video we just record, then we get to here. Okay? So that is consider. We can probably try one step and show you what is that. So okay, so we know that we can clearly see the x at the critical condition, or we can write chi at critical condition. Whenever it's a chi, I put the 2 dashes below it, so you know it's what I'm written is actually chi, right? So, okay. So, this would be how does chi relate to the ball of refraction? Well, x1. Or basically, how does these two is related? So at this position, what it would be the chi is. Okay? So what can you learn from this? Xc equals 2 multiplied by x1 squared divided by 1. If you remember long time ago, when we start talking about this, we actually define what is chi is, or Flory-Huggins parameter. We defined x in terms of interaction parameter, W12, W11, and W22, the interaction parameter between different components of your material, right? We have that part. And in that class, we define the chi of your material is defined as number of nearest neighbor is this z. Delta W is the temperature before and after you had the interaction energy, or delta W is equals to W12 minus half of W11 minus W22. So that's the interaction of solvent AA, solvent BB, and that's the interaction of AB. That we did while we calculated entropy of our mixing. You should have the note. And K, TC, T, not TC. K is a constant. C is again, T is the temperature. So that's how we define the chi. And that's actually somehow interrelated. Using this equation, we can convert a relationship between the x and t. In other words, if we put these two together, we can basically get z delta W divided by kt. I'm just repeating this equation. Going to be equals to, at the critical temperature, at Tc, will be equals to the equation above. So you can get what is Tc is, right? You can get what Tc is. So Tc, if you move the Tc to here, 2 chi squared to there, what you will get is it's going to be equals z delta W and 2z delta x1 squared divided by k. That will be it. That will be defining what would be the Tc is. And because, while Daniel said at the beginning of class, because if you look at this equation, our material is more or less symmetric. And the xc will be equals to 1.5 in this case. Where if you put in the xc, let's put the x. When this equals to half, you can get what is critical temperature. 0.5 squared will be a quarter. And this multiplied by a quarter will be z delta W 2 k would be what the critical temperature in the material system if it's a small molecular Wins blended. Okay? So in this way, we obtain what is the connection between the Tc and the chi in this particular material system.
What was Z again?
Which one?
Z.
Z is how many nearest neighbor in the packing. So while we define the entropy, we define Z multiplied by delta W in the interaction parameter will be equal to the entropy, enthalpy before and after mix, right? It's just the nearest neighbor. You can think about in the reality case, in the example we gave, Z actually would be equals to 12, which means one molecule, you only need to consider the neighbor's packing of 12 molecules around it. Okay? Okay, so now this is a time for you guys to ask questions. Critical point for a binary case, because in the next class we will do one more change. Is now in the next half class we will do Flory-Huggins for polymer, and you will see this equation need an update, and that will be influencing now this curve. And I can tell you this no longer be a symmetric one, but it will be skewed into one direction. Now it's a half-half bet, right? You can guess if it will be skewed over left or the left or the right. So I'll ask you guys to think about what this would be the case. So in other way, so now what would be the new phase diagram? For polymer A in solvent B. So 0, 1, this is going to be volume fraction of the solvent. Oh, sorry, this should be the volume fraction of polymer, means it's a dilute polymer solution. So while you're going from here to here, means you're getting a concentrated polymer solution. Now the question is, will the phase diagram look like this or look like this? Let's call it scenario 1 or scenario 2, because once you consider connectivity, it will influence thermodynamics of delta G and influence your results. So we're going to take a break and come back to see what is Flory-Huggins theory for polymer influence your results. And we already know, in this case, the entropy contribution for the polymer, this need an update because it's no longer N2, right? It will be, it's going to be another N term here, and which is, if you consider persistent, N2 need to multiply by a degree of polymerization N before that. If you consider Pilates side, then you will have, I still want to write it down, or we can write it x1 log x1 plus x2 divided by n log x2 plus x1 x2, and this is chi if you consider Pilates side. So this n term is making a huge difference whenever you have considered the polymer case. And in the next half of the class, we will see how does a polymer influence a phase diagram. This is still like a preliminary, as we start with just a solvent. And next class will be more fun. Okay, we can take a 5 minutes break. Then we come back, talk about what is what is polymer influence. It's vaguely defined as degree of polymerization, and yeah. Yeah.
re-explain how you translated this to this? I'm not quite following.
Yeah, no problem. So
I understand that it's isothermal.
So yeah, so what this one is, it's actually, this axis is key because the bottom axis is the same. It's both plot xc or x or volume fraction, right? Or volume fraction of minor component, which means, well, you put a little bit A into B and put the half A into B and put mostly A into B, right? So this is delta G. That's the definition of delta G, right? N1 log x1 plus N2 log x2 plus this. You can see this, if you think about this is Y, this is X. It's a little bit complicated equation, but it will give you this plot, right? This is the energy, delta G depend on volume fraction of the blend.
So did you draw this using only this equation, or did you draw this from this?
No, only this equation.
Okay.
So that's the origin, how you get it here.
That makes sense, because I was trying to look at this one and interpret this one, and you can't do that.
No, you actually the other way. You use this to get this,
Okay.
not the other way around.
Okay, because I couldn't figure out how you went from that to that.
No,
and then
it's
you went from that. Okay.
no, it should be.
Gotcha.
We get the Flory, now the lattice theory. We use the lattice theory to get what is delta G dependent on the x. Or this, you can think about. It's a complicated mathematical equation. Y equals to x. X changes from 0 to 1 will give you a curve.
These are both negatives because they're fractions.
Which one?
ln 0.5, ln 0.5. That's going to be negative, and then you have the
Right.
this guy.
Right. So this is dependent on temperature. So that's why when you change the temperature, this delta G will also change. Right?
I see.
So if you change the temperature, then it might look like this way, because T will influence this delta G as well. So now let's figure out one delta G. So then look at this curve. What we do is now we take second derivative. It's called Spinodal point, which is just these 2 points, right? You can get these 2 points. Now you use these 2 data, put it here. At this T, you got 2 data points. That's what you can do, right?
Take the third derivative to get the maximum.
Yeah. Or you need to also change the temperature, get a different temperature, you get a new curve, then you got 2 new data points. You change another temperature, so you need to change multiple temperature until you get a smooth curve.
Okay.
Does that make sense? Okay.
Yeah, that makes a lot more sense. Thank you.
Yeah.
What are you looking at?
It was like nobody was watching it. It was just him doing it for his own amusement, and I was just like, Jesus Christ, get me kind of together. Oh, sorry, I was murdering my round on him.
What are you talking about?
Yeah, one of my lab mates. So like sometimes when he'll wash his round bottoms, he'll like sink them in the base bath or whatever. You know how it bubbles when you sink them.
Yeah.
So one day he was doing that, and nobody was watching him. So and like I just happened to be walking by, and he just quietly goes shh 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 shh. Don't struggle. It's like, Kevin. He's like, oh, I was murdering my round.
Kevin,
bottom.
like her Kevin?
Yeah, her Kevin.
You're dating a serial killer.
Yes.
In other news, I got locked in the bathroom stall just now, and I was panicking.
It's the second one.
Yes.
You just gotta lean against the wall a little bit. Show it.
I was like sitting there like this, and I was like, I'm stuck.
This is me now. This is where I
I
live.
was so panicked, and the stalls are kind of low, so you have to like really drop down if you want to crawl out. And I was like, this is where I live.
This is
Throw
how
me
I
a
died.
pillow.
This is how I died. So
This is Hannah, our resident stall PhD.
We just throw flasks in there and give her some stuff, whatever she needs. She does them over the sun.
She can only do reactions in an art bath. She has a toilet.
who all is passing out candy tomorrow night? Anybody?
Well,
Dr. Gu, are you taking it? How many children do you have?
One.
One.
Yeah.
It's a son, right?
Yeah.
And he's 2?
2.5.
Are you taking him trick or treating?
Yes, I think so.
What's his costume? Sorry, 20 questions.
we are thinking about several options, and he had one of them is what I can call it. He dressed like a lobster. It's a very famous. It's coming from a movie. You guys may watch it called Love Actually. It's a movie. Inside the movie, they actually had one of the little kids was dressed like a lobster. They have an opera show. That was inspiring coming from. And the other one, I think mom has different opinion, and she is figuring something else as well. Let's see how it unfolds.
So she'll probably go with her idea.
Let's see.
I think lobster sounds adorable.
Lobster sounds cute.
Yeah.
Yeah, bring pictures on Thursday.
My daughter
I will
wants to
try.
right now, so I might just turn. Well, thing is, you can't really turn the lights off because trick-or-treating starts at 4. What? Yeah. The official times are 4 to 7.
So we get this bar.
Says the sheriff of Hattiesburg in Lamar County.
I think everybody should come over to our house and pass out candy with us, and we'll just terrify the kids because they'll open the door. There'll be 13 just.
You know what would be a fun thing to watch is next day, check the YouTube. They always like prank video for the parents tell the kids all the candies are done.
You should do that to your
I found it hilarious.
You have bushes in front of your house? Yes, we've had the bushes pop out. They're not, but they're big.
I think we should. Everybody should come over and pass out candy with us.
Yeah, I'm gonna work on my presentation.
I know. The kids in the kindergarten, they're gonna walk around the campus tomorrow.
Oh, really?
Yeah.
I think they're.
I didn't know what time they said, but the teacher said, get the kids dressed because they're gonna walk around. I asked her, are they gonna stop by the Palmer building? But
I hope so.
no, no, you have to catch them. Okay, so let's start the second half of the class where we now learned all the tricks about this phase diagram, spinodal, binodal, critical temperature, etc. However, everything we did is just on solvent case, but we are again in polymer department. We need to solve the polymer problem. So that's where the second half of the course is about. What does the phase diagram for a polymer look like? And use the next 30 minutes to 40 minutes, we will go through quickly what is a phase diagram. And lastly, I'm going to answer a very important question. X1 we can easily understand and comprehend. It's just a molar volume fraction for one of the component. How much you put in is basically what is x1, and 1 minus x1 is basically this axis. But if you see more of this type of curve, this parameter seems very important. And I believe we chatted a little bit about what is chi. But we never went very deep about actually how do you, is there a better understanding what these chi parameters are, or Flory-Huggins. So if we have some more time, we will go through what is Flory-Huggins parameter. All right, let's get started. So I'll remove some of the part to give it some room. So for the polymer, we will get delta G will be equals to x1 ln x1 plus x2 . So this would be the chi, and if we do a mu or chemical potential, or this will be delta G. Oh, I'm missing RT here. So if you take a delta G, first the derivative again, x1, that will be give you the chemical potential. And we're going to do it again, except now we have an interesting n term contributing to the entropy contribution of x2. But you will soon see it's actually make a huge difference. So this will be very much similar, because again it will be log x1, x2, 1 minus. This is going to be the chi, x2 squared. So we're going to do one more derivative. But now we're going to get it to this equation. No, this should be x2. So that's pretty close where we want to get to where, because this is the second derivative of that. If you take one more derivative, if we will be able to get the critical point, right? So if we do one more time of this curve, mu1, RT twice, x1 squared, so the critical point we basically can get from this a little bit long equation. Okay, so if we could get from what is Spinodal composition from the XC, which we can get, Spinodal composition is defined from here, right? So this is second derivative of delta G. This is basically defined as Spinodal decomposition, where you can get chi and x1, x2 relationship. So let's take a look what is the conclusion from the Flory-Huggins theory. So in other words, it's x1c will be equals to 1 plus root n. So that's where the critical composition is at, or the critical point. In the first case, we talked about this. This is for polymer. We also have for solvent, right? For solvent A plus B, we basically get x1c is equal to 1/2, or in other words, this is always symmetric. This critical point is always right at the center. But now we see for the polymer solvent case, if you take a special case, if n equals to 1, this would be, again, comes back to this, which means you still get critical point is at the half. But once you have a polymer, degree of polymerization, n will be much larger than 1. So think about this as 100. Then the x1c will be, let's say, give a case, n equals to 100. x1c will be equals to 1 plus root of 100 divided by 1. So this is about around 0.9. So in other words, if you have a polymer we immediately see x1c is shifted into the left side, whereas what is this case? Now x1c is roughly there.
This is for a polymer in solution.
Yeah, for a polymer in solution.
And is the degree of polymerization?
Yeah. So again, in outside this, it will be. So in other words, in our last point we gave, actually number one situation will be the case for the polymer mixture. This will be two-phase, right? And you can kind of rationalize by yourself by walking around this curve. So if you have a little bit of polymer in solvent, they're going to mix. But if you put more, they might be precipitate and phase separate into two phases. That's what this a little bit skewed plot means. Okay? And that's where this end turn made a lot of difference between a polymer and non-polymer system, right? Okay? Everybody still with me? With what kind? How does it influence the critical point? And we gave an example if n is equal to 100. So in some textbooks, because root n, it will be likely much larger than 1. So they can even simplify this to be x1c will be equals to root m1 divided by root n, because this will become negligible. So degree of polymerization is making a lot of difference for the phase diagram. If putting a super high molecular weight, your phase diagram will very much squeeze to the left, close to the x equal to 0. If your degree of polymerization is 1, you kind of come back to this curve, right? So if I get a different color, I'll try to make my point more clear. So if you have n equals to 10, this will be something look like this. The white is n equals to 100. And if it's even higher polymerization, it won't be a sharp peak, but something look like this. Your phase diagram is more or less cramped in one way, coming from the fact that this equation. Okay? Any question on this point? Okay, so now how about chi at critical temperature? It will be equals to okay, so that's chi c at critical temperature. What you need to do is just put into this equation. You can get what this chi c is. Oh, actually, we put this one into here. Okay, then chi c will equals to this. You can get what the chi is. Now, use this. We can understand what is how does the phase diagram for a polymer solvent mixture looks like. Because due to the connectivity, your phase diagram is no longer oriented in one way, but it's going to be shifting on the direction. Okay? And use the last few minutes, I want to come back to what is chi. Because what is chi c, or what is chi is one of the most parameters in the phase diagram. Chi determines a lot of things. And in the essence of your polymer mixed with solvent, you will see this part is entropy contribution is more or less differs not that much between different polymer and solvent. Let's say polystyrene in toluene or PEO in DMF. they have similar lattice side and molecular. The difference is just going to be the molecular weight, so this might be different. But this very much term is so different between different polymer. And use the next about 20 minutes, I'll try to explain what is chi. And how do we interpret this is rather abstract number or term into real physical meanings. So let's look at here. What is chi for you guys? What we learned so far? That's the name. And any more information you want to say?
I mean, you threw a couple equations at us.
Uh-huh.
V delta W over kT, part of the enthalpy term.
Yes, and the delta W